we're going to be talking about alternating series. Now, alternating series is a series where we're summing up this infinite collection of terms, and the terms change sign from plus to minus continually. So, given bk, which are always positive, so I'm going to abbreviate alternating series to alt series, is an expression like this. It's the sum from k equals 1 to infinity, minus 1 to the k minus 1, and then bk. So this k minus 1 is just because by convention we want the first term to be going forward, but it's completely not important. We could also have minus 1 to the k, and that's going to be the same thing so long as it converges. We just pull out the minus 1. Okay? So don't be interested or too concerned about this k minus 1, why it's here. It's completely unimportant. All right, so that's an alternating series. So let's try and visualize what it does. So it's a good idea to think about a series as doing this infinite collection of steps and trying to have some notion of where you'll end up at infinity. So if we start from here, so this is us, and we're going to go forward by b1, okay? And then we're going to go backwards by b2. Maybe I change color. So we go backwards by b2. This is b2. And then we're going to go forward by b3. And then backwards by b4. And so on. Okay? So we are forever going to go forwards, backwards, forwards, backwards, forwards, backwards. And we want some notion of what happens after doing infinitely many steps like this. All right, so let us perhaps just give an example of such a series. So, example. The sum from k is equal to 1 to infinity minus 1 to the k over k. This is an alternating series. Notice this time I start with k instead of k minus 1, but it makes no difference at all. Well, obviously it makes a difference to the answer, but it doesn't make a difference to the nature of an alternating series. Okay? All right, so alternating series are a little bit different in that previously, when we've been considering series with just positive terms, we've had to think quite carefully about when it will converge. And we've learned the classic example of the sum of 1 over k does not converge, right, by the integral test. And the sum of 1 over k squared does converge. In fact, the sum of 1 over k, 1 plus anything, any other power, any 1.1 does converge. So the example of the sum of 1 over k is kind of key because that's just slow enough to fail to converge. And any higher power does converge. Well, all that stuff is no longer relevant here because it turns out if you have an alternating series, you don't care about these terms slowly going to zero, going fast enough to 0. You just need them to go to 0. So this is the main theorem. Given an alt series, then series converges if the following two things hold true. 1, bk plus 1 is less than or equal to bk, okay, i.e. decreasing. And secondly, the limit as k tends to infinity of bk equals 0. So we know this has to be true for it to converge, because if it's not true, then there's no chance by the divergence test. We're very happy with this. Okay, so we just need it to be decreasing and the limit to go down to 0, and then the thing will actually converge. And the reason why is very simple. It's, as always, it's just a picture. However, the reason why is also why the alternating series estimate result holds true. So rather than explain the same thing twice, we'll just leave that as a fact for the time being, and then we'll do some examples of checking whether or not we can conclude a series converges. And then we'll explain something slightly more sophisticated, which is that we can actually estimate very easily how close the partial sum is to the actual series itself, which is something we've learned to do with the integral test when we have positive terms, but it's somehow even easier if we have an alternating series. So that's one of the things we'll see. But let's just, for the time being, start with some examples. So, well, we started with this example. We can see that this clearly satisfies the test, right? So in this case, bk is 1 over k, clearly decreasing, clearly the limit as k goes to infinity is 0, so converges by the theorem, okay? Let's do another example. So let's take this series, the sum from k equals 1 to infinity, minus 1 to the k squared over k squared plus k plus 1. Okay, so in this case, the bk are just this k squared plus k plus 1, and the limit of the bk is just going to be 1, the dominant term, top and bottom of the k squared, so it can't possibly converge. So if we try and think about what this series is doing, for very, very large k, these numbers are as close as you like to being 1. So basically all we're doing with this series is going forward by something close to 1, then backwards by something close to 1, and forwards by something close to 1, and backwards. And then we do this infinitely many times. It has no meaning, right? There's no possible thing this can be. It's not any number at all. So it does not converge. Okay, so let's do another example. Let's see if I can squeeze it down here. Change pen. What about pink? No, I'm not going to be able to squeeze it in. Okay, let's erase the board. So let's consider this example. Sum from k is equal to 1 to infinity, minus 1 to the k, square root of k over 2k plus 3. Okay, so solution. What do we need? Well, the bk are these terms, square root of k, 2k plus 3. We need them to tend to 0 as k tends to infinity, because again, if for any series, if those terms don't tend to 0, then there's no way it can converge. And sure enough, it does, because k is blowing up much faster than the square root of k. So yeah, these terms do tend to 0. So the limit as k goes to infinity, bk for sure is 0. And we also need them to be decreasing, okay? And that isn't so completely obvious, right? So what are we going to do? Well, the most easy way to check if a sequence is decreasing is simply to create a function that recovers the sequence and then check the function is decreasing. It's one of the powers that we have now that we have this machine of calculus. So this is what I mean. So if you have a sequence, here's 1, here's 2, here's 3, here's 4, and so on, a sequence of positive terms, you can represent each term of the sequence just as, say, some dot above the integers. 3, 4, and so on. And if we create a function that goes through all of these dots and is decreasing, then for sure the sequence of dots is decreasing, right? So in the language of math, what's that? We need f such that f of k recovers this, the square root of k over 2k plus 3, and it's obvious what the f has to be. It's f of x is equal to square root of x over 2x plus 3. And now we just need to check that this f will be decreasing, so need f prime to be less than 0, and maybe not just straight away, but after some point on the real line, if it's decreasing from that point onwards, then our sequence of points is going to be decreasing, so our sequence bk of numbers will be decreasing, and that's good enough because, as we've said a number of times, convergence of a series doesn't care about the first finite number of terms, no matter how many there are. So if we have some issue about not being able to check this thing is decreasing for the first 5 million terms, we don't care, because if they're decreasing from 5 million onwards, then that's good enough to apply the alternating series test, and we know it converges. So we need to check that this thing is actually got negative derivative, so we're just going to calculate it. So put it here. F prime of x, we apply the quotient rule, everything over the bottom squared. Differentiate the top, leave the bottom alone. Leave the top alone, differentiate the bottom. Okay, so what do we get when we clean this up? Then we are just going to get, from here we're just going to get square root of x, but we're going to subtract minus 2 square root of x, so we're just going to have minus square root of x. And then from this term right here, we're going to have plus 3 over 2 square root of x, like this, over 2x plus 3 squared. We don't care about the stuff in the bottom, it's definitely positive. And since as x grows, for sure, this thing goes down to 0 and this thing increases, then just making an obvious estimate. If, for example, x is 4, then this guy's going to be minus 2, and this thing is going to be something less than 1. So from that point onwards, it's going to be negative. So this is less than 0 for all x bigger than or equal to 2. And then we've got this thing is decreasing from 2 onwards, and that's good enough. Okay, so the bk are decreasing. And so series converges by the alternating series test. So actually checking that we have convergence is pretty straightforward. All right, so okay, let's talk about why the alternating series test is true, or theorem is true. So, why is theorem true? Okay, so, as always, as I said before, it comes down to the picture. And this is what we're going to do. So, let's take bk equal to 0, and we're going to form this thing. Let's first take the partial sum Sm. So it's the sum from k is equal to 1 up to n of minus 1 to the k minus 1 bk. Okay, let's define it this way. And let's try and see what it actually does. So we've made this convention of putting the k minus 1, so it's going to, as the first step, it's going to go forward. So we start here. This is us. And we start, and we're going to go forward by b1. And then we're going to go backwards by b2. So by that I mean this distance here that we've traveled is b1, and then this distance here is b2. Okay, and then we'll continue doing this, forward, backward, forward, backward, forward, backward. Okay, suppose after the nth step we end up here. So this is the nth step, and let's assume that that n is even. So this is going backwards by bn, and then we are right here. Okay. So this particular point here is exactly Sn. So here we are. This is Sn. This is where we are after doing n steps, right? We do our first step, 1, 2, 3, 4, blah, 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 n, and that's our nth step. That's where we are. Okay. And then what? Well, then we're going to go forward again, right? Because we're alternating. If we go forward, let's change color, we go forward by bn plus 1. Like this. But bn plus 1 is actually less than bn, so we don't go as far as this. We stop somewhere before then. So then this is bn plus 1. Okay. So in class, I usually ask for a couple of volunteers. I have no volunteers here, so I've got a couple of props. I have the board cleaner and I have a bottle of beer. Okay, so let's make the board cleaner where we are at the Sn step. Okay, and the bottle of beer is where we are at the bn plus 1 step. Okay, so this is where we are at the bn plus 1 step. And then if we continue, what's going to happen? Well, we are now going to go backwards by bn plus 2. Right? So we go backwards by bn plus 2 from this position here. Yeah? But we won't go as far as where we were on the nth step, because we've gone forward by bn plus 1, we go backwards by bn plus 2, but bn plus 2 is less than bn plus 1. So we're trapped between where we are at the nth step and where we are at the nth plus 1 step, which is here. So maybe I put that also. So the nth plus 1 step, this is where we are. Okay, so we do this bn plus 2, and we're trapped between these two steps, or these 2 points. And now we're going to go forward by bn plus 3. But we don't go as far as where we were before, because bn plus 3 is less than bn plus 2. So this is where we were on the nth step. We take this bn plus 1 step, we arrive here. Then we take the step backwards, but we don't end up as far as we were before. Then we take the step forward, and we don't end up as far as we were before there. Then we step backwards, and every time we do this step, we are always going to be trapped between the board cleaner and the bottle of beer. Right? This will happen indefinitely. We will never be able to escape these things. And every time the step we take is smaller. Right? So you can see that as we do this infinite number of steps, we have to be converging to some sort of answer. Right? As we keep doing more and more of these steps, we're just taking tinier and tinier steps forwards, backwards, forwards, backwards, forwards, backwards. And ultimately, at infinity, we will arrive at some particular point here, and that'll be our actual answer. Right? That'll be the actual sum. Okay? So, I'll just move the beer bottle so I can write down what this is. This will be the sum from k is equal to 1 to infinity, minus 1 to k minus 1, bk. This is the actual answer, and that is just the limit of the partial sums, and it will be somewhere like this. It definitely has to exist. This limit has to exist. Right? Cool. So that's the reason why this limit exists, but it also gives us more, because this thing here is the actual answer. This is the thing that we seek, right? So, right? And we can't actually do anything infinitely many times. So what can we do in practice? In practice, we can just calculate something a finite number of times. If you're doing this in a computer program, you're going to run the program, adding, subtracting these quantities for as long as you have computer memory, for as long as you want to run it. You'll end up at some finite place, right? But in practice, you would like to know how close you've actually got to the real answer. And that quantity is the distance between the Sn step and the actual answer, which is this distance right here. Right? It's this distance right here. But it's trapped between where we were, the Sn step, and where we are after moving forward by Bn plus 1, i.e. the Sn plus 1 step. So it's trapped between the board cleaner and the beer bottle, in other words. Yeah? Cool. So let's run through it again. What have we done? Starting our alternating series, go forwards, backwards, forwards, backwards, forwards, backwards. On the nth step, we end up here. Okay? Then we take a step forward by step size Bn plus 1. We end up right here. Okay? And then we go backwards, but we don't end up going as far backwards as where we were before. So we're somewhere here. And then we take a step forwards, and we don't go as far forwards as we were before. Then step backwards, then step forwards, then step backwards, then step forwards. And in infinity, we are somewhere between the board cleaner and the bottle of beer. And that distance is the size of the Bn plus 1 step. Okay? So it tells us that if we want to know how close we are to the actual answer for doing n steps, that is less than the size of the Bn plus 1 step. Cool. And that is just pictures. This is just a picture, nothing else. So let's express what I just said in the language of math. So if we let S be the actual sum, k equals 1 to infinity, I mean, defined it down there, or I wrote it down there, we see that S minus Sn is less than Bn plus 1. Cool. This right here is S. All right. And that's incredibly useful. That's an incredibly useful and rather simple estimate. Problems that happen, as I say many times in class and will say many times speaking here, is that if you don't know why this is the estimate, you will misremember it and apply it wrongly. If you go through this procedure for yourself, convince yourself that this is true drawing these pictures, then you won't. This will be meaningful to you, you'll know why it's true, you'll feel confident in applying it. And I think the confidence in applying it is a big plus. If you know why something is meaningful, then you can apply it. It's not just like doing some sort of magic where you hope you did the steps in the right order. You just see why it's the case. All right, super. So that is why the theorem is true, and that's an additional theorem. So let me call this a theorem 2. So theorem, we see that this is true, that the difference between the actual sum and the nth partial sum is less than the size of the n plus 1 step. And that allows us to actually calculate these things. Let's do an example. So, put this stuff away. So this is example. Let me change colors. Calculate the sum from use k equals 1 to infinity minus 1, the k plus 1 over k to the 6 to within 0.00005. Okay, solution. Well, 0.00005, what is it? So this is the 1 over 10, this is the 1 over 100, this is 1 over 1,000, this is 1 over 10,000. We have 5 this over here, so it's actually 1 over 20,000. Okay? And we know from the theorem that if we let bk be these numbers, 1 over k to the k to the 6, then what we need is n such that bn plus 1 is actually less than equal to 1 over 20,000. Okay, so let's continue things over here. So bn plus 1 is 1 over n plus 1 to the power 6. We want this to be less than 1 over 20,000. Flipping things around, we want 20,000 to be less than or equal to n plus 1 to the power 6. So let's find out what the 6th root of 20,000 is. And that is like 5 point something something. So 5.21001 is very close to the 6th root of 20,000. Okay, up to some decimal place, and we want this to be therefore less than n plus 1. So we ask ourselves, what n can we choose such that this is true? So clearly n is 5 is the correct thing. Now obviously if we had n is 6 it would also be true, but the point of these questions whenever it says calculate some quantity like this to within this error, it doesn't want you to do more work than you actually have to do. So if, well, once you calculate n is 5, then what would you do? You would just add up the first 5 terms of this, which I'm not actually going to do, but we could actually do it. It's just at this point a task which is accessible to human endeavor, right? So we would just say, thus, whatever this is, when we take the sum from k equals 1 to 5 of minus 1 to the k plus 1 over k to the 6 is the answer. Is answer. And that is basically it for alternating series. The main thing to take away is that this thing that has been drilled into you at this point, that you have to consider how quickly the terms go to 0 in a series, that's not true anymore. We just need these things to go to 0 at any rate, okay? To be decreasing and to go to 0 at any rate for this reason. Here, we don't care how slowly the bn go to 0, it's just enough that they go to 0, right? You know, because the partial sum Sn will indeed get closer and closer to some particular answer, and that will be the limit. In fact, we even know the difference between the Sn and the answer. It's less than the bk plus 1 or bn plus 1 term, and n is tending to 0, so that's all we need to know. Okay.